So let's take a look at calculating limits using the limit laws. Suppose that you have two functions f of x and g of x, and so you have the limit of one of the functions f of x as x approaches some value a, and you have the limit of the other function g of x as x approaches that same value a as well, and suppose both of those limits exist. So given that information, let's go ahead and look at the actual limit laws. So for the first law here, let's say we're trying to take the limit of one of the functions f of x plus g of x as x approaches that same value a. Then what we can do to evaluate this is take the individual limit of both functions. So we take the limit of f of x as x approaches a, and then plus the limit of g of x as x approaches a as well, and that's how we can evaluate this specific limit. Now for number 2, we have the limit of this time not f of x plus g of x, but we have f of x minus g of x. Well, it's going to work the exact same way. As x approaches a, we can go ahead and evaluate by taking the limit of each individual function. So the limit of, if I go ahead and write the limit of f of x as x approaches a, instead of a plus this time we're going to have a minus, so the limit of f of x minus the limit of g of x as x also approaches a. So now for number 3, let's say we have the limit of some constant c times f of x as x approaches a. Well, the way we can evaluate this, since c is just a constant, we can go ahead and actually put that outside of the limit. So we can evaluate by saying c times the limit of f of x as x approaches a. So once again, you can only take the c outside only if it's a constant. Now for number 4, we have the limit of f of x times g of x as x approaches a. So the way you can evaluate this using the limit laws is, once again, you can take the limit of each individual function. So you take the limit of f of x as x approaches a multiplied by the limit of g of x as x approaches a as well. And then for number 5, this time we have the limit of f of x divided by g of x as x approaches a. Well, the same process here, the same as multiplication, but instead we're going to divide. So we take the limit of f of x of each individual function, so this time f of x as x approaches a, divided by the limit of the other function g of x as x approaches a as well. And just make sure that the limit of g of x as x approaches a does not equal 0, because if it equals 0, then we're basically dividing by 0, and obviously we can't do that. So another restriction we had to put is also that the limit of g of x as x approaches a cannot be equal to 0. So for this first set of problems, given that the limit of f of x as x approaches a is equal to -3, the limit that g of x as x approaches a is equal to 0, and the limit of h of x as x approaches a is equal to 8, find the limits that exist. So for the first part, part A, we have the limit of f of x plus h of x as x approaches a. Now once again, in order to evaluate this, we can use the limit laws and take the limit of each individual function, so both f of x and h of x. So we can go ahead and say the limit of f of x as x approaches a plus the limit of h of x as x approaches a as well, since there is a plus sign that separates f of x and h of x, the two functions. Now the limit of f of x as x approaches a is obviously -3, and the limit of h of x as x approaches a is obviously 8. So we can go ahead and take -3 plus 8, which will give us the answer of 5. So the limit is going to be 5. So now for letter B, we have the limit of f of x squared as x approaches a. Well, how could we solve this? Well, the easiest way to do this is to first find the limit of just f of x itself as x approaches a, and then square that entire value. So what is the limit of f of x as x approaches a? Well, that's obviously -3. So we can go ahead and take -3 and square it, so we'll get the limit as 9. So now for letter C, we have the limit of the cube root of h of x as x approaches a. So the same process as last time. Let's go ahead and first find the limit of just the function h of x itself as x approaches a, and then cube root the entire thing. So first, the limit of h of x as x approaches a is obviously going to be 8. So then we can go ahead and take the cube root of 8, and the cube root of 8 gives us the limit of 2. Now for letter D, we have the limit of 1 over f of x as x approaches a. Now realize that 1 is a constant, f of x is the function. We're not really trying to take the limit of 1, we're trying to take the limit of f of x. So we can put 1 outside of the limit and say 1 over the limit of just f of x as x approaches a. So then we get 1 on the numerator, and then the limit of f of x as x approaches a is obviously negative 3, so our final answer is going to be negative 1/3. For letter E now, we have the limit of f of x over h of x as x approaches a. Because we have two functions, f of x divided by h of x, we can go ahead and take the limit of each individual one. So we first take the limit of f of x as x approaches a, and then divide that by the limit of h of x as x approaches a. So the limit of f of x as x approaches a is going to be negative 3. So we take negative 3 divided by the limit of h of x as x approaches a, which is 8. So the final answer is negative 3/8. So now for letter F, we have the limit of this time g of x over f of x as x approaches a. Once again, we can go ahead and rewrite it using the limit laws as the limit of g of x, the top function, as x approaches a, divided by the limit of the other function f of x as x approaches a. So the limit of g of x as x approaches a is 0, and the limit of f of x as x approaches a is negative 3. So we have 0 over negative 3, which is obviously just 0. So now for letter G, we have the limit of f of x over g of x as x approaches a. Once again, we can go ahead and rewrite it as the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. Now the limit of f of x as x approaches a once again is negative 3. The limit of g of x as x approaches a this time is 0. So once again, we cannot divide by 0, so we have to say that the limit does not exist. So now for letter H, we have the limit of 2 times f of x over h of x minus f of x as x approaches a. Now the way we can evaluate this is, since we have a function on the numerator and denominator of the fraction, we can go ahead and first set it up as the limit of what's on the numerator, so the limit of 2 times f of x as x approaches a, and then divided by the limit of h of x minus f of x as x approaches a. Now for the numerator, because 2 is just a constant, I can take that outside of the limit. So I can rewrite it as, on the numerator, we have 2 times the limit of f of x as x approaches a, and then divided by, because we have two functions being subtracted, or we have h of x minus f of x, we can go ahead and say the limit of h of x as x approaches a minus the limit of f of x as x approaches a. So now all we have left to do is plug in numbers. So obviously we have 2 outside as a constant, so we have 2 times the limit of f of x as x approaches a, which is negative 3. So we have 2 times negative 3 on the numerator, divided by the limit of h of x as x approaches a, which is 8. So we have 8, and then we have a minus the limit of f of x as x approaches a, which is obviously negative 3. So we have 8 minus a negative 3, which is the same thing as 8 plus 3. So our final answer, 2 times negative 3 is negative 6, divided by 8 plus 3, which is 11. So we have negative 6 over 11. So now for the next set of questions, we're going to be looking at trying to evaluate the limits of actual functions rather than just f of x, g of x, and h of x. And so the first step you always take when evaluating limits is direct substitution. So let's say you have the limit of f of x as x approaches a. Well, what direct substitution is we're going to go ahead and substitute that a value directly into x. So we basically have f of a. And that's not always going to work, but that's always the first step you have to take when evaluating limits. And if that doesn't work, we have to try other methods. So now for number 1, we have the limit of 1 plus 3x over 1 plus 4x squared plus 3x to the 4th, the entire thing taken to the 3rd power as x approaches 1. Now this might look like a lot, but all we're doing is, once again, we're going to first start with direct substitution to evaluate this limit. So we're going to plug in 1 for x into the entire function. So let's go ahead and plug in 1. Now if I do that, we will get 1 plus 3 times 1 is 3 over 1 plus 4 times 1 squared is just 4 times 1, which is 4, plus 3 times 1 to the 4th, that's just going to be 3 times 1, which is 3, and the entire thing taken to the 3rd power. So if simplifying the inner fraction here, 1 plus 3 is 4 over 1 plus 4 is 5 plus 3 is 8 to the 3rd power. 4 over 8 can obviously be simplified to 1/2, so we have 1/2 to the 3rd power, which is going to give us 1 over 8. And that's the final answer. So now for number 2, we have the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. So now the first step is obviously direct substitution, so let's go ahead and directly substitute 2 in for x into the function. So when I do that, we'll get 2 squared, which is going to be 4, plus 2 minus 6 over, we get x is equal to 2, so 2 minus 2. Now 4 plus 2 is 6, 6 minus 6 is 0, over 2 minus 2, which is also 0. So because we got 0 over 0, and obviously we cannot divide by 0, that tells us that direct substitution does not work. However, that does not tell us that the limit actually does not exist. So I'm actually going to go ahead and go back to the original function and try to simplify this function, then use direct substitution again to see if the limit exists. So if I go ahead and erase this, I'm just going to go ahead and simplify x squared plus x minus 6 over x minus 2. Now how could we do that? Well, once again, we have a trinomial on the numerator, so we can go ahead and actually factor that. Now I need two factors, or two numbers, that will multiply to negative 6 and add to positive 1. Well, I'm thinking about negative 2 and positive 3. So I can go ahead and rewrite the numerator, x squared plus x minus 6, as x minus 2 times x plus 3. And then we obviously have over x minus 2 on the denominator, so divided by x minus 2. Now realize both of these are the same factors, x minus 2 and x minus 2, so they can cancel from both the numerator and denominator. So all we have left is x plus 3. So now I can go ahead and rewrite the limit. So we can rewrite it as the limit. We have simplified this entire thing down to x plus 3. So we can rewrite it as the limit of x plus 3 as x approaches 2. So now I can go ahead and use direct substitution and substitute in 2 for x, or 2 back into the function. So we get 2 plus 3, which gives us the limit of 5. So now for number 3, we have the limit as x approaches 2 of this time x squared minus x plus 6 over x minus 2. So obviously if we use direct substitution, we'll get 2 minus 2 on the denominator, and that's 0. We can't divide by 0, so we have to try to use another method to prove that the limit does or does not exist. So I'm going to go ahead and try to simplify this function, but realize we can't actually simplify this function, because if we try to factor the numerator, I need two numbers that multiply to positive 6 and add to negative 1. And there are no two numbers that actually do that. So this fraction cannot actually be simplified. Well, how could we find another way to prove that the limit does or does not exist? Well, remember that for the limit, let's go ahead and just call it f of x, for the limit of a function f of x to actually exist as x approaches some value a. The limit from the left-hand side, so the limit of f of x as x approaches a from the left-hand side must be equal to the limit of f of x as x approaches a from the right-hand side. So in other words, the left-hand and right-hand limits must be the same in order for the actual limit to exist. So if we apply it to this limit here, let's see if the limit of x squared minus x plus 6 over x minus 2 as x approaches 2 from the left-hand side is equal to the limit of the same function, x squared minus x plus 6 over x minus 2 as x approaches 2 from the right-hand side. And if both of these are equal, we can go ahead and assume that the actual limit does exist. But once again, if they are not equal, then the limit actually does not exist. So let's go ahead and first test out the limit as x approaches 2 from the left-hand side. So because we're approaching 2 from the left-hand side, we need to try to pick an x value that is less than 2 and that we can directly substitute into the function. So let's go ahead and pick an x value of 1. So if I go ahead and directly substitute in 1 for x into the function, we get 1 squared, which is 1, minus 1 plus 6 over 1 minus 2. So then we get 1 minus 1, which is 0, plus 6, which is 6, over 1 minus 2, which is negative 1. So then we get negative 6. So now let's go ahead and test the right-hand limit and pick an x value that's greater than 2. So let's go ahead and pick 3 and plug that into the function. So we get 3 squared minus 3 plus 6 over 3 minus 2. 3 squared is 9, 9 minus 3 is 6, 6 plus 6 is 12. So we get 12 over 3 minus 2, which is 1. So then we get our answer of 12. Now obviously negative 6 does not equal to 12, which tells us the left-hand limit and the right-hand limit are not the same. So that tells us that the actual limit of x squared minus x plus 6 over x minus 2 as x approaches the value of 2 does not exist. Now if you're allowed to, and if you're trying to test the limit out, you can also try and graph this function. So if I go ahead and graph x squared minus x plus 6 over x minus 2 on a graphing calculator, I'll get something like this, where let's say this is the x value of 2. You will get something like this. So obviously the limit from the left-hand side does not equal the limit from the right-hand side. So we can also assume by using a graphing calculator that the limit does not exist. So now for number 4, we have the limit as t approaches negative 3 of t squared minus 9 over 2t squared plus 7t plus 3. Obviously direct substitution comes first, so let's go ahead and plug in negative 3 for t into the function. So when I do that, we'll get negative 3 squared, which is 9. So we get 9 minus 9 over 2 times negative 3 squared, or in other words 2 times 9, which is 18. We get plus 7 times negative 3 is negative 21, and then plus 3. So then 9 minus 9 is 0 over negative 21 plus 3 is minus 18, or negative 18, and then 18 minus 18 is 0. Obviously we cannot divide by 0, so we cannot say the limit does not exist, but we can say that direct substitution does not work. So we have to try to go back to the original function and try to simplify this entire thing if we can. Now on the numerator, t squared minus 9 is a difference of squares, so we can go ahead and factor that into t plus 3 and t minus 3. Now for the denominator, we can try and go ahead and factor this, so I need to multiply the a and the c term. In other words, 2 times 3 gives us 6. So I need two numbers I can multiply to 6 and add to 7. Well, that's obviously going to be 6 and 1. So I can say t plus 6 and then t plus 1. So now we need to go ahead and take the a term, which is 2, and divide the numbers by 2. So we have 6 over 2 and 1 over 2. Now if it comes out clean, then we can go ahead and write it as it is. So 6 over 2 is 3, so we can rewrite it as t plus 3. Now since 1/2 is not a whole number, I need to actually go ahead and move that 2 up front. So we have 2t plus 1. So that's how we factor this trinomial. So I'll rewrite 2t squared plus 7t plus 3 in factored form as t plus 3 times 2t plus 1. Realize that t plus 3 will cancel on the numerator and denominator, so we're left with t minus 3 over 2t plus 1. So now I can go ahead and rewrite the limit of t minus 3 over 2t plus 1, which is what we have simplified this entire fraction down into, as t approaches negative 3. So now we can use direct substitution and plug in negative 3 for t. So on the numerator we'll get negative 3 minus 3, and then on the denominator we'll get 2 times negative 3, which is negative 6, plus 1. Negative 3 minus 3 is negative 6, over negative 6 plus 1 is negative 5. Realize that negatives will cancel, and so our final answer is 6 over 5, which is the limit of this function. So now for number 5, we have the limit of 4 plus h squared minus 16 over h as h approaches 0. Now direct substitution, if we plug in 0 for h, we obviously will divide by 0, so we can't use that. Well, in order to simplify this fraction, or to simplify this entire function, I'm going to first go ahead and FOIL 4 plus h squared. So then we'll get 16 plus 8h plus h squared. We do have minus 16 outside, so minus 16 all over h. Realize that 16 and negative 16 will cancel, and so then we're left with 8 times h plus h squared over h. Now I can actually go ahead and factor out an h from the numerator, so we'll get h times 8 plus h over h. Realize that the h's will cancel, and so we're left with 8 plus h. So now I can go ahead and rewrite the limit as h approaches 0 of 8 plus h. Now we can use direct substitution, so when I plug in 0 for h, we just get 8 plus 0, which is going to be 8. So now for number 6, we have the limit as t approaches 9 of 9 minus t over 3 minus the square root of t. So using direct substitution, if we plug in 9 for t, we will get the square root of 9, which is 3, so then 3 minus 3 is 0. Obviously we can't divide by 0, so we have to find another way to evaluate this limit. Now realize that 9 minus t is actually a difference of squares. So we can factor that into 3 plus the square root of 3, or 3 plus the square root of t, times 3 minus the square root of t. And then obviously we do have 3 minus the square root of t on the denominator. Realize 3 minus the square root of t's will cancel, both on the numerator and denominator. So all we're left with is 3 plus the square root of t. So now I can go ahead and rewrite the limit as t approaches 9 of 3 plus the square root of t. If I go ahead and use direct substitution, we will get 3 plus the square root of 9, which is 3. So that'll give us the final answer of 6 as the limit. For number 7, we have the limit as x approaches 7 of the square root of x plus 2 minus 3 over x minus 7. Obviously direct substitution does not work because 7 minus 7 is 0. That will divide by 0. So let's go ahead and try to simplify this entire function. Now whenever you have something in the form of the square root of some function x, like x plus 2, and then plus or minus a constant, it's probably a good idea to multiply by the conjugate. So what that means is we just multiply by the same thing, just flip the signs. So we have the square root of x plus 2, this time plus 3, over the same value, so square root of x plus 2 plus 3. And then we can go ahead and FOIL. So go ahead and multiply numerator, and I'm not going to simplify the denominator. I'm just going to leave it as it is, multiplying these two. So on the numerator, I'll simplify. So when we FOIL, we get the square root of x plus 2 times the square root of x plus 2, which is just going to give us x plus 2. And then we have negative 3 times positive 3, which is negative 9. And then on the denominator, I'll just leave it as it is, so x minus 7 times the square root of x plus 2 plus 3. So now positive 2 minus 9 is obviously going to be negative 7. So we have x minus 7 on the numerator over x minus 7 times the square root of x plus 2 plus 3. And so now realize the x minus 7s will cancel. So that is the reason why I didn't simplify the denominator and I left it just as it is. So we're then left with 1 over the square root of x plus 2 plus 3. So now we can rewrite the limit as x approaches 7 of 1 over the square root of x plus 2 plus 3. And now I can use direct substitution. So when I do that, I'll get 1 over the square root of 7 plus 2, which is going to be 9. So the square root of 9 plus 3. Square root of 9 is 3, so we get 1 over 3 plus 3, which is 6, and that's the final answer. So now for number 8, we have the limit as x approaches negative 4 of 1 over 4 plus 1 over x over 4 plus x. Obviously direct substitution doesn't work because 4 plus a negative 4 is 0. We can't divide by 0. So let's go ahead and try to simplify this function. So first I'm going to go ahead and actually add those fractions together on the numerator. So for 1 over 4 plus 1 over x, the common denominator is going to be 4 times x, or 4x. So I'm going to go ahead and rewrite 1 over 4 as x over 4x, and then plus I'll rewrite 1 over x as 4 over 4x. Obviously we do have 4 plus x on the denominator, so I'll divide it by 4 plus x. So then simplifying the numerator, we just add the fractions together, so add the numerator, x plus 4, and then we have the common denominator of 4x, and we also divide that by 4 plus x. Now if I go ahead and rewrite that, we have x plus 4 over 4x. Now dividing by 4 plus x is the same thing as multiplying by its reciprocal. So we're going to go ahead and multiply by 1 over 4 plus x. Now realize x plus 4, 4 plus x are the exact same things, just rearrange the terms. They will cancel, and so we're just left with 1 over 4x. So then I can rewrite the limit as x approaches negative 4 of 1 over 4x. So now I can go ahead and use direct substitution, plug in negative 4 for x. So then we'll get 1 over 4 times negative 4, which is negative 16. So the final answer is going to be negative 1 over 16. Now obviously in the majority of the problems that we did in this video, direct substitution did not work initially. But even if it does not work for the majority of problems, you still make sure that you use direct substitution first.